Hi folks, today's lesson is entitled Strange Squares. The real purpose of the lesson, I think, is, well, what you'll be able to take away from it is a better knowledge of this relationship here. When you have a triangle with angles of 90 degrees, 45 and 45, you have this ratio, this relationship among the three sides. So you'll have a better working knowledge of that, but we're going to learn about that by kind of playing around in the coordinate plane. So let's start with something that everybody more or less knows, which is, if I think of this grid as having in between this point and this point a length of 1, which is arbitrary 1, that means that if this is 1 and this is 1 and I make a square, the area then in here is going to be 1, right? So that's not a big shock that we take 1 times 1 and get an area of 1. Okay, so we're set there. Okay, so this is a length of 1. Now, out of nowhere then comes what we call an irrational number, and it happens when we draw the distance from this point to this point. So we're going to jaywalk across the intersection, and suddenly we have an irrational number. Now, how do I know it's irrational? Well, that's a longer story, but you might remember the Pythagorean theorem. A squared plus b squared equals c squared, right? This applies to triangles that are right triangles, and that's what we have here. We have a right triangle. We have a triangle that is a right triangle, and it's isosceles, because remember, each of these is 1 because it's a square. So because we have these two equal sides, it's isosceles, and we have a right angle here. So it's a right triangle, and this is going to apply to it. So we can go ahead and say this is A, this is B, 1 squared plus 1 squared equals c squared. This is 1 plus 1. And then if I take the square root of both sides, technically I wind up with plus or minus the square root of 2, but I don't have to bother with the minus because I know I'm talking about a distance in the coordinate plane. It's an actual distance, so it has to be a positive number. So positive square root of 2. Now, what does this mean? I want to just first tackle this question. What is the square root of 2? What we mean when we say the square root of 2 is we mean the number that you can multiply to itself to actually get 2. That number exists. Now that number is not 1. 1 times 1 does not equal 2. Clearly that number is not 2 either. 2 times 2 does not equal 2. So that means it's somewhere in between 1 and 2. So what is this number? Well, it turns out it's not such a nice number to look at. It's approximately 1.41. So if I do 1.41 times 1.41, it'll be close to 2. It'll be, you know, maybe a little bit less, 1.9 something or other. If I want to get a product that is exactly 2 on the nose, I got to make it a lot more precise. So something times itself equaling to 2, well, it's going to be 1.414, and then I'll be a little closer to 2, and if I keep going and going, I can get something that's very close to 2. But the thing is, I would never get a very exact number. I could never, like writing this out as a decimal, I could never make it something exact as a decimal expression to multiply to itself to make 2. That's what we mean by irrational. Okay, we can't really express it as a decimal that we can write out. We can't express it as a fraction with something over something. This is not equal to 3 over 2. This is not equal to 14 over 10 or any such thing. This cannot be expressed as a fraction. So it's kind of a mysterious number, but we know it exists. We know it's out there. We know there's a number that you can multiply to itself to make 2, and it's very close to this. Okay, so that's what you need to know right now. It's not a number that we can express very easily without simply just writing this symbol, which I already had here, and I'm going to write it again, square root of 2, right? So that's what we mean when we write this. The number times itself that equals 2. Okay, so quite a bit of ado there, just to write square root of 2 as the length of my diagonal. Okay, so here's where we were. We had 1, and now we have the square root of 2. Okay, now, that means that if I connect these dots, this will also be the square root of 2, as will this and this. So now I have my first strange square. This is a square because all the sides are equal. And that's not the only thing that makes it a square. It might have all equal sides and not be a square. But I know that it is because since this is 45 degrees and so is this, that has to be 90 and likewise all the way around. So the angles have to be equal as well as the sides. Okay, so big question now. I fill this in. I fill in my square. What's the area? Give you a minute to think about that. What is the area of this square? Thought long enough? Okay. Well, if you figured it out, the area is 2. The area of this square is exactly 2, not approximately 2. It's exactly 2, which means, that's right, if I fill in 2 of these squares, I have exactly the same area. If you don't count this, this pie crust that I have to cut off here, I have exactly the same area as I do if I make this square right here and fill it in. Exactly the same. The area is exactly 2. And you could probably explain why if you caught on to the last thing that we were saying about the square root of 2, which is that it is the number that I can multiply to itself to get 2. Well, what is area other than length times width? This is one dimension, this is another. Root 2 times root 2 gives me the area, which is 2. Okay, so first I had my square of area 1, which is red. Now I have my square of area 2, which is blue. Okay, now, next up, let's draw the diagonal of our area 2 square. There's the diagonal. I connect corner to corner. What is the length of this diagonal? Do you see what the length is? The length of this diagonal is 2. We connected point to point. We're still relying on the scale that we started with here. This is 1, here's another one, we got a diagonal of 2. So I can certainly now make another square. Whoops. Let's go with yellow. I can certainly make another square based on that diagonal. If I draw out equal sides equal to that diagonal and I fill it in, I get a square. And of course, that square, and I'm going to, yellow is not really going to work for me. That square has sides of 2, which means the area is 4. So, first square red, area of 1. Second square blue, area of 2. Third square yellow, area of 4. Okay, now, suppose I continue this pattern. So let's go with green now. Okay, so, and I'm going to actually, you know what, I might have to start using the tool here. Oh, well, if it will let me. And, it kind of let me. Okay, maybe I won't do that again. Okay, so here we have a diagonal, it's green. What's the length of this diagonal? We connect this point to get the diagonal of the yellow square. What is it? Okay, so maybe now you're running back to your Pythagorean theorem. See what you can do with that. Okay, so that would be a length of 2 on one side of this isosceles right triangle and another length of 2 on the other side of this isosceles right triangle. Come on, don't fail me now. is equal to c squared. Okay, so 4 plus 4, right? 2 squared is 4. 2 squared is 4. I have 8. I have 8. So when I take the square root of both sides, I have c equals the square root of 8. Okay, so once again, what is that? It's the number that multiplies to itself to make 8. It's not 2. It's not 3. It's got to be in between 2 and 3 because 8's between 4 and 9. We got to multiply some number, 2 point something, times itself to get 8. We don't know what that is. The calculator can tell you. You can work it out on a piece of paper if you got a little bit of time and the inclination. But we can know just from this that it's somewhere in between 2 and 3. Now there's something else we can do with this radical. We call this a radical expression because it's underneath the square root sign. There's something else we can do with this radical expression, and that is to simplify it. We can say, look, 8 breaks into 4 and 2, of course. 4 times 2 is 8. I can take this radical and split it into 2 parts. Square root of 4, what number times itself equals 4? That would be 2. So the square root of 4 equals 2. I can bring this factor down, and I have 2 root 2. Now I can't simplify that part anymore, but look at this. This is a simplified radical expression. The square root of 8, whatever it is, it's going to equal our good old square root of 2 that we used before times 2. So it's double. In other words, we had square root of 2. Now this is 2 times square root of 2. And you can see that. Look at this. Obviously, this distance is twice as long as this distance. It's 2 of these put together. So this is 2 root 2. All right, let's get rid of some of this stuff here. All right. Okay, and now you can probably guess what I'm going to do next. Let's connect the dots here. And we've got ourselves a square, and the side of that square is 2 root 2. Okay, now, big moment here. I'm going to fill in the square. Here I go. Boom. Okay, now what question am I going to ask you? This pen. Area! What's the area of this square? Well, I don't know. Maybe has something to do with what we were talking about when we did the blue square. In case you didn't tell, I'm stalling to give you some time to figure it out before I just blurt it out. Okay, well, I've waited long enough. The area, of course, is 8. Okay, so why is the area 8? Because what's the length of this? Well, it's 2 root 2. And we're multiplying that times itself, and when you do that, you get 8. And that's, of course, true also because 2 root 2 is also the square root of 8, right? It's just this is a simplified form of this. So you're multiplying it to itself to get 8, right? Square root of 8 times itself, of course, equals 8. So we have the red square, which is area of 1, blue square, which is area of 2, yellow square, which is area of 4, and green square, which is area of 8. There are many patterns in what we're doing here that we may need to reveal very soon. Before we do that, let's see if we can go for the lightning round. Okay, couple more here. Diagonal, what's the length? Length is 4. We bring this out. We draw our square. What's going to be the area? 4 times 4? 16. Okay. What color's up next? Orange. We draw the diagonal. I can do better than that. Yep. Bring it on back. Okay. Whoops. I always do that. That's what I always do in my classroom, you know, and everybody thinks it's the funniest thing ever. Okay. So here we go. There we go. Okay. What's the length of this diagonal? Okay. Now, at this point, maybe we've started to notice a pattern. Let's say we have the side of the square, the diagonal, and the area. So let's make ourselves a table. The side was 1, diagonal was square root of 2, area was side times side, 1 times 1 was 1. Side of the blue square was root 2, diagonal was 2, area was root 2 times root 2, that was 2. Side of the yellow square was 2, diagonal 2 root 2, area was 2 times 2, that was 4. Side of the green square, 2 root 2. Diagonal was 4. Area, this, which is the square root of 8 times itself, area was 8. Okay, then we got the black square. Side is 4, area is 16. What's the diagonal? Well, you see the pattern here. Not only can we count on this as a sequence, it's multiplicative or geometric, we just multiply here to get the next one, but we can also multiply what we have, this is even more important, on this column, we can multiply by a certain number to get this. Every single time, we can multiply by the square root of 2. In other words, the side of this triangle, or you could say side of the square, multiply the square root of 2 by the square root of 2, gives you the diagonal, which is the hypotenuse of the right triangle that we're talking about. Okay? That's true here, 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 and here. Every one of these sides times the square root of 2 equals its corresponding diagonal. So we can just multiply this by the square root of 2. And that's what we're going to do. So here we have 4 root 2. Okay, so as you can see, we can continue this pattern of strange squares until we go just about off the page. We can continue our table here, and we can keep demonstrating to ourselves over and over again the same relationships. And we're not even mentioning all the patterns here. I'm sure you can see some more. But the main thing I want to focus on today is what we said, that for each of these side lengths, we can multiply by the square root of 2 to get the length of the diagonal. So suppose then we just look at any old isosceles right triangle. So we'll say this is isosceles right, these are 45s, and this is a 90-degree angle. So then if this is 12, well then, you know, since they're the same angles, these are the same sides, we can immediately know that's 12, and because of our pattern from the last page, we know that this length is 12 root 2. It's as simple as that, right? Now, not only that, but we can deal with stranger situations as well. If we have 45, 45, 90, and we have something like, oh, I don't know, 6 root 2 on a side, well, then we know this is 6 root 2, and we simply need to multiply by the square root of 2 to get the hypotenuse. So we can do that right here. 6 root 2 times the square root of 2. We can multiply these radicals together. We know that square root of 2 times square root of 2 is 2. So this is just 6 times 2. So that we would have simply 12 here as our hypotenuse length. Okay, so suppose I have an isosceles right triangle, and I know, let's say I know the length of the hypotenuse, let's say it's 50, and I want to know one of the legs, one of the other sides. Well, I know they're the same length, right? So this is a little bit different situation. I know they're the same length, so I could call this like A, for example, or I could call it X, or whatever letter I want, as long as I represent it the same, because I know these sides are the same length, right? Because these angles are the same. So A is fine. So if we call them both A, then we could say A, as we've said over and over again, A times the square root of 2, the side times the square root of 2, is going to equal the diagonal or the hypotenuse. So now the question is, what is this A? All right, well, one way to deal with this, why am I making a document? One way to deal with this is to simply solve it algebraically. We could just divide by the coefficient, A equals this, okay? And then you'd have to simplify that radical. So if you're comfortable doing that, then go ahead. I just want to look at the pattern one more time. What we've noticed so far is for when we have a side, and this is the diagonal or the hypotenuse, as the case may be here, we've seen such things as, if the side is 4 root 2, the diagonal wound up to be 8. When the side was 8 root 2, we had a diagonal of 16. When the side was 6 root 2, we had a diagonal of 12. So by now, you're noticing what we're doing here is, in each case, we're multiplying by the square root of 2. Square root of 2 times itself, these two factors, gives you 2. 2 times 4 gives you the 8. Okay, well the same thing's happening here. Root 2 times root 2 is 2. 2 times 8 is the 16. Here, root 2 times root 2 is 2. 2 times the 6 is the 12. So now the question is, if we have 50 here, what is this? So that when we multiply the square root of 2, we get 50. Well, it's going to have root 2. And what do you suppose is the factor sitting right here? 25. So that these can multiply to make 2, to double the 25, to make the 50. So now we know the length of the legs.